Very good afternoon to all in one present here. Respected Professor Sharma, the esteemed speaker for this afternoon, my colleagues from the department, the participants from various institutes of Northeast India and also the other parts of the country. I welcome you all to this public talk organized by the Department of Physics, Assam University, Silchar, as a part of Silver Jubilee celebration of the department. At the outset, I request Professor D. Indrajit Sharma, HOD, Department of Physics, to welcome the gathering in this occasion. Professor Sharma, please.
Thank you, Professor Atri. It is our great fortunate for Department of Physics to have Professor Dipankar Das Sarma this evening. Professor D.D. Sarma is a popular among the academic communities as a scientist and teaching the students. This evening, we are fortunate to have Professor D.D. Sarma. All of us are eager to hear this popular talk, Energy Crisis and Wonder Materials. This topic has its own great meaning. Let us know from his talk. Once again, Department of Physics, welcome Professor D.D. Sarma this evening. Thank you, Professor D.D. Sarma. Over to Atri.
Thank you, Professor Indrajit. And as we all know that the Department of Physics, Assam University, Silchar, is celebrating the Silver Jubilee this academic year. And as a part of celebration, we are trying to organize at least every alternate month one popular lecture in physics. So this started with a locally organized talk for the Comet Neos, and we were having just a locally organized program from the department in the month of July. Then September we had one popular talk delivered by Professor Anjan Ananda Sen from CTP Jamia, who talked in the dark side of the universe. And now we are here with Professor D.D. Sharma on energy crisis and the wonder material. So before we start, I have the privilege to introduce Professor Sharma before the gathering. Professor Sharma is now currently a professor at Solid State and Structural Chemistry Unit of Indian Institute of Science, Bangalore. He is also an honorary professor of Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, also of Essenbush Center for Basic Sciences, Kolkata, and he is also an eminent visiting fellow of Indian Association for Cultivation of Science, Kolkata. He is known for his researches in the fields of solid-state chemistry, spectroscopy, condensed matter physics, material science, and nanoscience. Professor Sharma is credited with extensive research on nanomaterials and strongly correlated materials. His contribution is reported in discovering the existence of a new phase in solid-state materials through high-energy spectroscopies and theory. His researches have been documented by way of several articles published in various peer-reviewed journals. According to online repositories, he has almost 656 articles published so far, and this H index is around 43 and I-10 index is around 167. These are numbers just I am quoting, and he has almost over 20,000 citations. And he holds more than 16 patents in his credit, and obviously he has guided a good number of PhD theses so far. So Professor Sharma was born in Kolkata in the year 1955, and he has got his master's from IIT Kanpur in 1977, IIT Kharagpur, right? Kanpur. So IIT Kharagpur in 1977, and he has got his PhD from IISc Bangalore in the year 1882 under the supervision of Professor C.N.R. Rao. He worked as a research associate at IISc for a year, and then he moved to Jubilee Research Center, Germany, as a guest scientist in 1984. He has returned to IISc as a lecturer in 1986, and then he remained there until he became a professor in the year 1999. Till then, he is a professor there. He was in prestigious Jain Tata Chair Professor till last month. Professor Sharma has received uh, lots of laurels throughout his career. It started possibly with Sir Gyanachandra Ghosh Memorial Gold Medal at IIT Kharagpur in 1981. Then Young Scientists Medal from Indian National Science Academy in 1983. UNESCO awarded him the biennial Javed Hussain Prize in 1989, and a year later, in 1990, he received the Medal of Excellence from the Material Research Society of India. The Government of India awarded him the Shanti Swarup Bhatnagar Award in 1994, and he received the C.V. Raman Award in 2004. In 2005, he bagged three prestigious awards: the Hariom Ashram Trust Award by UGC, the G.D. Barola Award, and Alumnus Award for Excellence in Research from the Indian Institutes of Science. He received the Federation of Indian Chambers of Commerce and Industries Award in 2006, the TWAS Prize in Physics awarded by World Academy of Sciences in 2007, National Research Award in 2009, H.K. Firodia Award in 2013. He was honored with the Knight of the Order of Star of Italy in 2014 and an honorary doctorate from the Faculty of Science and Technology at Uppsala University, Sweden in 2015. So, to name a few only. So Professor Sharma is an elected fellow of American Physical Society, the Academy of Sciences for the Developing World, the National Academy of Sciences India, and the Indian Academy of Sciences. And he also holds the fellowship of the Asia Pacific Academy of Materials. He is also an J.C. Bose National Fellow as well as Homi Bhabha Fellow. So Professor Sharma has held a number of academic positions in India and abroad throughout his career. Besides heading the solid state and structural chemistry unit, he served as a guest professor in the Uppsala University, Sweden, a distinguished scientist at the CSIR Network Institutes of Solar Energy, an honorary professor at the Jawaharlal Nehru Center of Advanced Scientific Research, Bangalore, and a distinguished visiting professor at IISc, Kolkata. He has also been an adjunct professor at the TIFR, Mumbai, twice during the period 2003 to 2014. He was associated with Indian Association for Cultivation of Sciences as a distinguished visiting professor from 2004 to 2014 in 2 terms. He also has been the adjunct professor in the Indian Institute of Science Education and Research, Kolkata, a senior associate for S.N. Bose National Center for Basic Sciences from 2003 to 2006, a member of faculty at the UGC DAE Consortium for Scientific Research, and an MLS chair professor at the Center of Advanced Materials. So Professor Sharma is a member of many professional bodies such as Council of Raja Center for Advanced Technology, Indore, the steering committee of the Sophisticated Analytical Instrument Facilities Program of the Department of Science and Technology, Government of India, and the Academic Advisory Committee of the Jawaharlal Nehru Center for Advanced Scientific Research, and is the coordinator of the group set up by Government of India for India's collaboration with International Center for Synchrotron Light for experimental science applications in the Middle East. So these are to name a few. It's a long list, and our participants, Professor Sharma is a known name to all, and I don't want to spend more time on this because this information all are available in public. I'm grateful that Professor Sharma has accepted our invitation to speak to the audience this afternoon. And without wasting much time, in other words, I would like to request Professor Sharma to please share his thoughts in energy crisis under wonder material. I again request the participants to keep the audio and camera in mute mode throughout the speech. If you have any question, you can put it in the chat box. After the talk, we will pick it up from there and we will put it to Professor for, his answer or his views. So with this, I request Professor Sharma to please start.
Thank you, Professor Deshmukhia, for a rather long and very embarrassing introduction. In fact, in between, I was seriously looking for a way that whether I could mute you from my end, and I found that against your name, when I clicked trying to mute you, it said that you cannot remove this participant. So you have a privilege. Otherwise, I'd have surely.
We are the organizers. I wish I could score some more, but I don't want to waste time.
No, before I start formally, I must tell all the students there, now that your teacher has given you a long lesson, let me start asking you questions on what she just now told you. Anyway, let's get back to the more serious business. I'm really very happy, except for the very embarrassing long introduction, very kind introduction, Professor Deshmukhi, I must say, and Professor Sharma. And I'm also thankful to my dear friend, Professor Sudhakar Panda, who actually made it possible by putting me in contact with Professor Deshmukhi for this public lecture. And let me get on with the lecture, and please feel free to type in your question. I'll try to answer them to the best of my ability. I'm going to disconnect the video for the time being because when I'm in the presentation mode, I don't get to see anything anyhow, and it will save the bandwidth, and maybe it will be better if at least the response will be better when I'm trying to show something. I'll come back again with the video on at the end of the talk. So now let me make presentation and a window. Okay. I hope you are able to see my screen.
It's coming, sir.
It's coming? Okay, fine. So let me get started. The title of the talk has already been pointed out. I'm going to talk about the energy crisis and a wonder material. My affiliation has been talked about, and I'm very happy to acknowledge the support, major support from Indian Institute of Science, as well as the Department of Science and Technology, and as a part of that ACRB as well, and a private fund that had supported us for 3 years till recently, Jamshedji Tata Trust, for very generous support that makes it possible for us to do what we do. And this wonder material that I have promised to talk about is really a new generation of photovoltaic material, which is some almost miraculous properties, which I'll come back at the end. And to specify the material I'll be talking about, it will be organic, inorganic, hybrid perovskite. Do not worry if you don't understand what it is. It will be my job to make you understand what I'm going to talk about. But a large part of the talk I'm going to spend on this energy crisis, because that's much talked about and often less understood. And I would like to give my perspective over the next 45 minutes to 50 minutes, what really I think the crisis is. And the plan of the talk is going to be, of course, I have to define what I mean by energy, particularly in terms of the usage and components of it that I'm concerned about in today's talk. Then I'm going to state what the problem is, or the crisis that I've talked about. And every crisis throws up certain challenges. And so I'm going to talk about how we'll be rising up, or we are trying to rise up to meet the challenges. And then some of the success stories in our attempt to meet these challenges, I'll talk about. Then I'll talk about specifically in the context of electricity generation, because energy is a very wide spectrum term, and I'll narrow down in terms of electricity generation as a particular aspect of energy, and I'll define the role of photovoltaics there. And then within photovoltaics, I'll introduce this new material class that I call the wonder material, and then I'll talk about what we understand and what we don't understand about this new material class. So essentially the idea is that I'll start with a very broad spectrum defining energy, what the crisis is, and narrow down and focus down through a specific material and tell you at the end what are the things that we understand and what are the things we don't understand and why we are so excited about it. I also start with a disclaimer that some of the my ex-student, Dr. Sharda Govinda, helped me in making many of the transparencies. And a few of the transparencies I've stolen from my very dear friend, Wolfgang Eberhardt and Professor Prashant Kamat. Now, let me get started by talking about the energy in terms of usage and components. One thing that we must keep in mind, that energy is absolutely essential for civilization. Not energy in terms, every living being needs energy in terms of food, for example. Animal kingdom, anywhere you need food for reproduction, for propagation of your species. I'm talking about beyond that, the civilization, our standard of living, which is far beyond just mere food, etc., needs energy constantly. In fact, it's so integrated into our progress that if you plot along the x-axis, the per capita GDP of a country, the gross domestic product, which is sort of an indicator of, let's say, the affluence of a country. And in the y-axis, you plot for the same country what is the kilowatt hour or the energy consumption per person. You can see for the year 2016, these are the different dots representing different countries. The size of the dot is supposed to show you the population. Do not worry about the population yet. I'll introduce that in a later slide. But what you'd see that roughly everything is going along this diagonal direction, which means if you want to increase your affluence in terms of the gross domestic product per capita per person, then you also need to go up in the per capita consumption of energy. So energy consumption and the progress or affluence of a society seem to be integrated together in a monotonic dependence of increase. Now, energy can come in very many forms. The source of energy can be, for example, oil, which we burn. The chemical energy of oil can be converted into different forms of energy that our civilization requires. Likewise, natural gas, coal, biomass, nuclear, various renewable ones, wind, solar, biofuels, hydro, and geothermal ones. And this is the actual requirement in terms of quadrillion British thermal unit of energy in 2016. And these are the projection how the energy requirement goes up. This gives you an idea where the energy is coming from. And you can see most of the energy requirement of the civilization today is coming from oil, natural gas, and coal, which we call the conventional source, because that's the traditional source from which we are drawing energy for our civilization's progress. And these are also the non-renewable. Once you burn the oil, it's gone. The natural gas, once you burn, or the coal, it turns into ashes. And there's no way of getting back the coal that you started off with, and that's why it's non-renewable. Whereas these ones, where the energy consumption or energy production from these sources is much less, those are the renewable ones, simply because the wind and the solar keeps coming every day. We are not going to exhaust it in a day, and so, or in a lifetime, or in many centuries also, and those are the renewable ones. So this is the source of our input of our energy that's coming from. Now, these different sources are used differently. Of course, energy, there's a lot of background noise. May I request people to keep their microphone muted? Okay, thank you. So the source of energy, different sources of energy are required for different kinds of utilities. For example, if I talk about transportation, of course, as we can see, green showing oil component, it's dominated. So transportation, whatever energy I need for the transport sector almost entirely comes from oil. Similarly, if I talk about electricity generation, you can see coal, for example, India depends completely on coal for the electricity generation, is a major component. And now natural gas has also become an important component, but oil contributes very little. So depending on which sector I'm talking about, my requirement of the input of energy changes its character to the oil, natural gas, coal, nuclear, biomass, and other renewables. So if I want to if I have a crisis, let's say of oil, then I need to look at transportation sector, because that's the one that is using mainly the oil. If I have problem in the use of coal for some reason, then I know it's the electricity generation that depends heavily on coal. So I should look for alternate ways of generating electricity. So it depends. The reason I'm telling you this, that means if I have to plan for saving any of these conventional or non-renewable sources, I need to know where it is being used. Yes, is there a question? Okay, I need to know which sector it is being used, and accordingly I must do my planning. And in these various sector of utilization of energy, it's clear that the electricity generation is the largest sector. And that's the reason why later in my talk, I'll focus down on electricity generation as the main one, because most of the energy consumption, as you can see, comes in the electricity generation aspect. Now that I have talked about energy, let me introduce the problem. Where really is the problem? Now this plot I have shown you, I've told you that everybody, and it's a legitimate aspiration of every country, that it wants to be more affluent. You cannot tell a country that has a very low gross domestic product down here that please don't spend energy and start move this way. Everybody wants to move this way, and it seems it's a necessity, then you must consume more energy. And you'd see that half of the global population, which is shown over here, has very low energy consumption per capita and also very low gross domestic product. And this half of the remaining half is consuming most of the energy and also have most of the gross domestic product per capita. So if this half of the global population have a legitimate aspiration of moving this way, then what would happen? Let us try to understand that. This is a plot only for 2016. You can see this is a plot over the years for just India. And you can see India surely wants to be more affluent, and its kilowatt hour per person per year consumption systematically goes up year to year simply because we are becoming more affluent. In fact, there's a 5% increase every year. And if you want to step up and start to produce and become a bigger player, more important player, financially stronger, then this 5% increase will have to become 10%, 15% increase per year. What will then be the consequence? This is the scenario per year for some of the countries for the year 2016. This is United States, using so many thousands terawatts or quadrillion watt hour of energy. This is whole of Europe together. This is China, and color coding is where the source is. For example, oil is very little. It has a lot of oil, coal, natural gas, etc. China here, India here, others here, Middle East, Africa, and rest of the world. Now, if I put the population that I talked about before in billions, these are the populations for these areas. Now, see the disparity. USA, with its population, which is about 1/4 of India, but on the other hand, it is using 4 times the total energy that India is using. So if India begins to consume per capita energy the same as a standard average American, then our energy consumption will become 16 times more, which means it will go out of the scale completely. Likewise, you cannot tell China not to use energy to make progress. Theirs also will go completely out of scale even today. So the energy requirement will be so huge that you cannot even imagine. And we are marching towards that. These are the projections going from 2016, 2025, and 2040. You can see how the energy consumptions is expected to grow from one unit to the other, one period to the other, demanding more and more energy. And this kind of thought precisely had led Mahatma Gandhi to reflect this statement when he said it took Britain half the resources of this planet to achieve its prosperity. How many planets will India require for development? We have only one planet. And so if everybody wants to have the same level of consumption, we're going to face a tremendous demand of energy. There are some costs to pay. It's not just that we're going to run out of these resources. Earlier, we thought when we were young that it's going to run out very soon. Then we found new novel sources. Now it is believed that it's not going to run out so quickly. But does it mean that we don't have a crisis? Let us look at the consequences. For every decision, there's a consequence. For every action, there's a reaction. When you use these sources, when you burn these gases and fuels, oils and coal, we give out, as you know, this carbon dioxide, nitrous oxide gases. Starting from the starting of the birth of Christ, the modern English calendar, if you look at the emission of these noxious gases, you'd see that they remained completely flat till very recently, and then suddenly started to zoom up very fast, and in this region, extremely fast. Why did it begin suddenly to increase here? Let me mark the year there. This is the 1760 to 1840. Those of you who remember the lesson of history, you know these are exactly the years that define the Industrial Revolution. An Industrial Revolution required energy for the mode of production. We shifted from agrarian society into an industrial society, and that required huge input of energy. And that required lot of burning of fuels, and that gave rise to the emission of greenhouse gases, very rapidly increasing. This is 1900, and this very steep part from 1900 to 2020, I'm going to expand in the next slide and try to understand this was a very big rise. Is there any structure within this narrow region? And you'll find when I do that 1900 to 2015 up here, that it's not flat. In fact, that steep rise in this scale first looks rather flat, then absolutely flat, and then from this point it started growing. What happened here? What happened is the Second World War ended, 1945, and then post-war, the tremendous industrialization and automation came in, and industrial growth drove economy even faster, and we started to have this increase. This increase seemed to show a certain flattening out here, as you can see. But after that flattening out, something again happened that led to this huge increase in the emission of gases. And I was trying to understand what this is due to. And when I came across a plot, which is as a function of year, something on this axis that matched exactly this growth. And let me tell you what this plot is. This plot is Chinese share of the world economy in percentage. And you can see that when Chinese economy started catching up with the developed world and wanted to become a world economical power, how it contributed to the greenhouse, this going up. And now if India also wants to join the race, we are going to push up. And nobody can deny our right to do so. And therefore, there's going to be heavy amount of this emission from fossil fuels. What is the consequence of fossil fuel emission? Some pictorial demonstration of the same area in 1921, the area that used to be always glaciers, 2009, you can see that the glaciers have completely melted. The global warming has affected us very, very strongly. Here is another glacier, the same picture from 1900 to 2000. There's no trace of glacier at any time anymore at this place. In fact, 50% of the glaciers have vanished from the face of the earth since 1850 till about beginning of 2000. Not only that, these also give rise to particulate matter. And as you know right now, there's a huge amount of pollution in northern India. In fact, this is a map of the concentration of particulate matter PM2.5, which is a 2.5 micron particle, micrograms per meter cube. And you can see the color coding. There's very bad pollution that's going on. There was this very famous study published in Planet Health in 2018. Some of the data are a little old. It's 2018-2019 data, but they had pointed out here that, in fact, if you look at the numbers here, you'd know that the World Health Organization says what is the limit of safe limit of particulate matter. It's 10 microgram per cubic meter. No state in India belongs to that regime. Everybody has more than 10 microgram per meter cube. India's own standard is 40 microgram per cubic meter. And 77% of India's population is exposed to particulate matter higher than that most of the time throughout the year, meaning that it is endangering our life. In fact, this Lancet paper that I talked about traces 1 in every 8 deaths in India to the pollution in India. And this is the price, heavy price that you are paying. So the energy crisis question is not whether we are going to run out of the conventional sources. Of course, the very fact that we have limited resources of conventional sources, we will run out. We can debate how long before we run out. But that's not the only question. The question is that whether we should continue with the conventional sources, because you have seen the cost and the sustainability questions that come up using this energy to the conventional source. Are we ready to pay this price? And the sustainability is being questioned. And then we might, global weather change, global ecological shift can cause problems which are completely unanticipated and may wipe out the human race because of some pandemic or some crazy changes in the atmospheric situation. Are we ready to face that? And we need to act today. That's why also, if it runs out, because we need petroleum not only for the transport, but for metallurgical reasons, and like coal is needed, petrochemical is a huge industry, and that cannot do without petroleum. And you want to save these precious natural resources for places that cannot be replaced, whereas electricity, transport have alternative sources of energy, as I'll be talking about after this. So really the controversy, the debate is between non-renewable versus renewable, polluting versus non-polluting, destructive versus sustainable, invasive versus non-invasive. And to my mind, it's very clear what we should opt for. And having talked about the crisis and the challenges that it is throwing, let me talk about how we may rise up to meet these challenges. So what the challenges are? The challenge is, so the crisis I've talked about, let me define the challenge. What I'm showing you, what is called the power generation mix. This is the electricity generation mix, power generation mix in terms of percentage coming from different sources. As you can see from 1970 to 2010, 2018 here, it is more or less the same. Our dependency on oil has decreased. That has been taken up by a little bit of increase in the nuclear compared to here, little bit of increase in the gas. We were in 1970, our total power requirement, 70%, more than 70% was coming from the non-renewable, coal, gas, and oil. And when we come to 2018, it's about 60%. So the scenario hasn't changed qualitatively. Now, what is being challenged, the challenge that is being thrown to us is by 2050, reduce the non-renewable fossil fuel dependency from the 60%. See, from 1970 to nearly 2020, 50 years it has taken to reduce us by about 10%. Now we want to pull it down from 60% down to 30% by another 30% reduction dependency on the fossil fuels. And then this shortfall would be met by a tremendous increase in the renewable, which is take up 64% of the total power generation mix. This is the challenge that we are facing. And in fact, if you see that today in 2016, power generation over the entire world, coal dependency was this much and gas. Coal, gas, and hydro were the main sources. For India, as you know, our dependency on coal is much higher, and that causes the pollution a lot more. So in fact, we face an even greater crisis than the average world population. What are the renewable sources? Hydroelectricity is a very well-developed technology. In fact, 2007, already it's producing a great deal of power. And over the years till 2017, you can see it has made small progress, but the progress is slow and steady because this technology is well-established technology, not driven by so much by research now, but implementation. Whereas you can see wind power had a very small fraction in 2007. In 10 years, it has increased by a huge amount. To quantify this, we can see that the hydropower has increased in these 10 years by 37%, and the wind power has gone up by more than 440%. In fact, the solar power, which is this one, I didn't even bother to calculate that because it will be in 1000%, because you can see that solar power was almost non-existent here, and it has become sizable, becoming comparable to the wind power and competing. And that is a success story that I'll be coming to and slowly focus down on this tremendous rise of the photovoltaic. And that's why I've decided to talk about photovoltaic after a little while. Before I come to the photovoltaic, let me talk about a few of the success stories. I've painted a rather grim picture for you of all the challenges and the crises that you're facing and all the bad and black faces of the technological drive and consumption of energy. But we've also succeeded remarkably in many different ways. And let me, before saying that, point out what is the energy chain in terms of electricity generation. I'm leaving out for the time being transportation, though what I'm going to talk about also has a very huge impact on the transportation and other applications. The energy chain depends on three ends: generation, transmission, and utilization. So there is a thermal electricity generation station where I input coal, let us say. I input units, 100 unit of energy in the form of coal's chemical energy. It's burnt. 62 units, 62% is lost in the thermal power plant. It's only 38% of this energy is transmitted into the power line. Power lines are good. They don't lose so much. Only about 2 units are lost. Then it comes into the households. And in my childhood, we had these incandescent lamps, and that lost 34% of the unit as heat. Only 2% of the original unit is used as energy. So the efficiency of utilization was only 2%. The fact that it was losing so much of heat, I don't know, some of the old Sudhakar will remember. By mistake, when we touched the bulb to change when it got fused and we didn't wait for long enough, we really burnt our fingers because it used to be so hot, right? So all the power that we were given was coming out as heat, right, Sudhakar? We all have experienced that.
Yeah, we felt it, yeah. Yes.
So it's only 2% utilization, which is a terrible thing. I mean, it's such a precious commodity and you're using 2% of it. That's criminal. What can we do? So we need to change at every level where we have very bad utilization. So first of all, in the conversion, I have very bad conversion. I'm losing 62%. And then I'm in the conversion, I'm losing 62%, and consumption, again, I'm losing a huge amount. At the conversion end is what I'm going to talk about is photovoltaic. Now, photovoltaic cells convert the solar energy, which is a renewable source. I don't have to worry about its efficiency so much. It's for economical reason, and I'll come to that in a moment. But it has a much larger problem. I can have a thermal power plant running through the night, producing energy. But this will not produce energy when the sun is not shining, if it is a cloudy day or in the night. So the source of energy is intermittent. So I need to store the energy. When I generate it, excess amount I should generate. So that when I'm not generating, the storage must supply the energy. So I need very high amount of storage. And this is where I'll talk about batteries. So I'll talk about photovoltaic, I'll talk about batteries, and then I'll talk about LEDs, which have revolutionized the lighting technology. So these are the three things I'm going to talk about as the success stories. It's a very quiet revolution that is taking place. We don't even realize it, how much the market is being taken over by these, because it's happening in such a quiet way, but it's a true revolution. Look at this. This is a photovoltaic cell. How much the photovoltaic cell module costed me in dollars per watt of power that it could generate in 1976. And as I increase the power generation capacity, the scale of power generation for photovoltaic increased, power generation price per unit watt came down, as you can see. This development also is actually chronological. This is 1976, this is 2018. At this end, it costed me $70 for every watt, and now it costs me only quarter USD per watt in terms of the module cost, the capex. That over a 42 years, I have a reduction in cost by 280 times, which is a fantastic reduction in cost. Very few things I've seen such cost reduction over such a short period of time. Then the batteries that I talked about also has had a tremendous success. Every year, the cost per unit of energy, kilowatt hour that it can store, the cost of saving that much, storing that much of energy is dropping year to year on an average by 22%. Such that, and that is driven by the battery efficiency or energy density going up. Smaller batteries can now store higher and higher energy, and that is this plot showing how the energy, and this is the point that we want to reach by 2022 or 2025. And we're on our way, and the price per unit energy storage is coming down steadily. If we look at the cost of it, it was about $1,000 for every kilowatt hour 7 years ago, and by 2015 it came down by a factor of 4, and it's going down steadily ever since. And about LED, it's so remarkable that the cost per lumen, which is plotted over here, I had to put it in logarithmic scale, not in linear scale, which means this linear decrease in price is an exponential decrease in price. And that is driven by the fact that this linear increase of lumens per package, the flux per unit of LED, that has gone up exponentially. And this reduction, to start with, it was about $50 per lumen, and now it is 0.4 cent per lumen. So in this 37 years, it has reduced the cost per lumen by a factor of 12,500. And this has created such a market reach, which I show over here, that it is possibly the fastest penetration into the market by any product, any innovation that human history has seen. For example, if we look at the hybrid electric vehicles compared to the market penetration of solar, photovoltaic, and wind versus LED, 2010, the hybrid electric vehicles had 1% share. 2020, you see them on the road, and they are now 7%. By 2025, it's estimated to be 22%. Photovoltaic in 2010 was 12%. It's already reached 31%. And it's really remarkable that the entire world is trying to push up. The 51% of total generation of electricity would be from photovoltaic. But look at LEDs. It had a 1% market penetration. It is already at 70%. And by 2025, it would be almost the only source of energy, light of every kind that the world uses. So this is a really remarkable discovery and development that has happened. And now let me focus down on electricity generation, and I've already told you why I want to look at that and role of photovoltaics. There are many, many sources of renewable energy, and I'm saying that I'm going to look at photovoltaics. Besides what reasons I've already told you, let me also give you one interesting reason. Every basic research finds eventually its way into some application. And that typically we talk about an S-curve, which is the market penetration this way and research effort this way. When it is basic research, market penetration is very slow and a lot of effort is required. Then comes this very rapid development part where a lot of excitement is taking place, a lot of innovations happening, so the thing is coming into the market also. And then again comes a slow and steady build-up of market development and market penetration at a later stage. And if you see, photovoltaic in this curve is situated at the fastest changing point. So this is the most exciting field to work with, along with battery and fuel cells, as you can see, for material scientists and condensed matter scientists in general. So it's a very exciting field. And of course, solar energy is available all over the world in plenty. And it is said that if you take a very small area in sub-Saharan Africa or in Sahara, then that can light up the entire world if you know how to store and transmit that energy. In fact, India has a very ambitious photovoltaic solar power generation plan. By 2022, it aims to generate 175 gigawatt. When I looked up in I think it was 2018 or so, or early 2019, it had already reached 12 gigawatt with a 370% increase over the last 3 years of that. The tariff, the price has also come down and has become competitive with more conventional sources. So that tells you photovoltaic is a very interesting part. And let me tell you why we're excited about this wonder material within the photovoltaic. And the particular compound that I'm going to talk about, a class of compounds, those are called organic, inorganic, and that's a hybrid, meaning it has both organic and inorganic. And this specifies the structure, perovskites. Perovskite structure is a cubic structure where it has a typically ABX3 kind of formula, where the B, which is typically a metal ion, sits at the corner, 8 corners of the cube. X, which is typically oxygen or halides, sits at the edge centers of these edges of the cube. And A, which is most of the time another metal ion, sits at the center of the cube. That creates the structure. I'll not go into the detail, though this structure determines the electronic properties, which makes it so fascinating. And it has very many properties. I'll not talk about it. I mean, all kind of very exciting physics and chemistry have been done, and material science has been done with this perovskite structure. In today's talk, what I'm going to talk about is hybrid perovskites, where this metal ion that I said is normally a metal ion is actually replaced with an organic molecular ionic entity. And in this particular case, it's a methyl ammonium ion, and I'll talk about it in a moment. And that has given rise to very efficient photovoltaic applications. And today's technology that you have, the modules are all silicon based. And that's a very sophisticated semiconductor industry compatible production channel. Very expensive, costs a lot of energy. In fact, sometimes people ask, these modules, how much energy does it cost to make a module? Does a module actually produce that much of energy? So the energy auditing, is it positive or negative? Because it's so energy intensive. But these materials that I'm going to talk about can be made in solution in under 100 degrees centigrade. So it hardly needs any power. So it's also very energy efficient in its production. This is a crazy curve. You will not understand it, and you don't have to understand it. National Research Laboratory in Colorado keeps track of every technology that is devoted to photovoltaic cells. And they trace how the efficiency of a particular technology is going up year to year. So the x-axis is telling me the number of years, y-axis is telling me the efficiency of the cell, and each colored and symbol code connected by a line tells me how that particular technology is improving its efficiency with time. The one that I just now traced is actually the single crystal silicon. This one is a single crystal silicon technology. And you can see that it is improved over a period of time. And this is the multi-crystal one, the one that we normally use. And you can see it is slowly increasing. And if I want to underline that, let me just put a sort of an ellipse covering the technology. And this long axis, major axis of the ellipse, it has the slope of efficiency increase. So on an average, efficiency started from somewhere there and went up there in these many years. There's another technology called the thin film technology, which is this green one. And that has a slightly faster rise. And you can see ellipse is slightly more tilted, and it's improving. This low rise is absolutely important. That has what has made it commercially viable. I showed you this low rise in the efficiency has led to tremendous production and cost reduction. And this new material that I'm talking about, if I want to show you that, and that's marked here, that's this ellipse, and you can see how rapidly its efficiency is increasing compared to the efficiency increase in all other technologies. And that's why you can see that this tremendous increase in the efficiency is exciting the community enormously. This is the expanded form, and these are the points, and you can see that the ellipse is really tilted, showing a very large increase in efficiency. The highest efficiency it has reached now is in the order of 25.5%, which is really remarkable. Not only that it is such a remarkable efficiency, it also works as a very thin material. And that is very important, because if I have to make a very thick material, and all silicon technology requires a very thick silicon layer to be able to absorb, because silicon is a very poor absorber of light, of solar energy. And that's why people started to do these dye-sensitized solar cells, because they become much thinner, 10 micron length scale, the device length scale typically. Then somebody said, no, 10 micron is too huge. Let's make it solid state dye-sensitized solar cell. That became about 2 micron thick. Then came the extremely thin absorber solar cell, which is about 0.5 micron thick. And this new material that I'm talking about is this is between 0.5 and 2 micron, and this is now less than 0.5 micron thick. So you can see how thin a material I can do, because it's a fantastic absorber of solar light. A little bit of history of this material. This was originally researched by Miyasaka in 2006 to 2008, and nobody took interest in it because the efficiency that he found was very small. Not only it was very small, he even showed a 4% efficiency, but it was extremely unstable. It was in several minutes, it was gone, efficiency. The first sizable efficiency was reported 6.5% when it was used as a quantum dot sensitized solar cell. But the real revolution came with these two papers, this one, the first one, and next one is this, which showed 10% efficiency of these materials using this material, and everybody then sat up and started looking at it. Why is it so good? What makes this material so good? So let me tell you what is the basic structure of a solar cell. A solar cell, for example, a silicon solar cell, what you do is to create an NP junction by doping such that they have a positive and a negative part. So now if light comes in and if light gets absorbed, what it does is to create an electron and hole. When it creates an electron and hole, the electron feels this positive, so goes that side, and the hole feels the negative, comes this way. And so then the drift and the electron goes there, hole comes here, and then the current flows and in the external circuit, giving me power. So I can get current out by converting the electron and hole and driving the electron and hole, separating them by this, creating this PN junction in the silicon. Is that all? Well, what are the properties that we need? We need it to be a good absorber of light. Good absorber of light has two things. Solar cells must absorb the photon energy, right? The solar spectrum. Now, solar spectrum peaks somewhere in the energy spectrum around 1.2, 1.3, 1.4 electron volts. If I have a band gap that's much larger, then most of the solar spectrum will not be absorbed at all. So that's not a good material. Then it's okay, if you want to absorb everything, have a very small band gap. But a small band gap has a problem. The output voltage can never be larger than the band gap. So the voltage will be very low. So you'll create a lot of current because you're absorbing a lot of light, but your voltage is low. And since power, which determines the total energy, is voltage times current, voltage being low, again, will give you low energy. So there's a sort of an optimum band gap that is good, and that's in the order of 1.4 electron volts, let's say. And you can see this material actually has a 1.55 electron volt band gap, so very close to the ideal band gap. And also it absorbs very rapidly. Very thin material is needed to absorb completely all the solar radiation. Not only that, after it has absorbed and created the electron and hole, this electron and hole has very long diffusion length because I need to separate them. Hundreds of nanometers in this film, it can get separated, which is wonderful, and that is required. And since it has a large band gap, it also gives me a large open circuit voltage, and so I get more energy. So these are all very good things. So if it is all good, why do we worry about it? And I'll focus on the last 5 or 10 minutes to tell you a little bit about the science that we've been doing with this. And I'll not go through, there's a large number of people, large number of publications from our group. I'll not talk about all this. These are, if you're interested, since it's being recorded, you can follow up. But the work that I'm going to present are mainly driven by Sharda. Today, what I'm going to talk about, Sharda, Bhushan, and Ashutosh, and very strongly supported by the group of Vienna, and more recent work from BRC, a collaboration that I'll not be talking about, and very strongly supported by JNC group as well. And my own colleagues, Professor Anshu Pandey and Professor Gurrao, and their group members also contributed very significantly. The compound that I'm talking about, these corner atoms are lead. These are halide ions, and at the center I have put this methyl ammonium radical. This methyl ammonium radical, often we could take the Ma and call it Ma, and we replace it and call it MaPbX3, where X can be any of these. Now, one thing, the very first thing you notice that this Ma, methyl ammonium, is an asymmetric molecule. Asymmetric, which means it has a dipole necessarily, because it doesn't have a center of inversion, so it has a dipole. Now, if something has a dipole, that can be ferroelectric. And if it can be ferroelectric, then it can be fantastic for photovoltaic for the simple reason, and let me show you, and this is the question that Sharda asked very early, that these dipoles, do they arrange in a way to give rise to a polarity in the material? Now, why is polarity important? I said that silicon has this PN junction. So if you have an electron hole generated close to this junction, the holes will go to the negative side, electrons will come to the positive side. But if the electron and hole are generated far away from this, they don't feel the potential, so they can recombine and not give you any electricity. And so the efficiency goes down. But in a ferroelectric material, you have a ferroelectric polarization throughout. And that immediately tries to separate the electron and hole, and you don't have this problem of recombination, and so the efficiency should go up. So there's a whole community and a whole research field that is trying to work with ferroelectric material, but unfortunately most ferroelectric materials have very large band gap, and so the question is, this small band gap material that we are looking at here, is it ferroelectric or not? So that is one of the basic issues that we wanted to ask. Is it ferroelectric, or how are the dipoles arranged? If they are they ordered in a ferro or an anti-ferroelectric manner? And if they're not ordered, they're disordered, they can be dynamically disordered, or they can be static, glossy disordered. So we want to understand this part. Another thing that we want to understand is the excitonic binding energy. Now, excitonic binding energy is when I create this electron and hole. After absorption of the light, electron and hole, of course, attract each other. The energy of attraction is this binding energy. If this binding energy is very large compared to the thermal energy, then of course you cannot split it. So you cannot get the electricity outside. If the binding energy is small, then you can easily split them and get the electron and hole separate, and you will get an electricity. So it's very important to know if it is large and small, but unfortunately, estimates run from 2 to 100 MeV. And so we don't know if it is small or large with respect to the thermal energy. So let me start with the ordering of the dipoles. And in fact, what one can do is a PE loop measurement. It's just like a magnetization measurement, but a ferroelectric measurement where you apply an electric field and measure the electric polarization. If it is ferroelectric, it shows you this loop. And this is a well-known ferroelectric material, lead zirconium titanate. Another example, barium titanate. Also, you can see the loop that it opens. This is from our own work, a ferroelectric material which has a very low band gap. We published it here. Shamashish was the main person driving this. And you can again see the beautiful loop. When I look at the low temperature phase of this material, there is no such loop. The small gap that you're seeing is actually coming from some lossy technical aspect. Don't worry about it. It essentially says the polarization and the applied field are proportional to each other. So it's a paraelectric material. At low temperature, I actually know the dipoles are aligned antiferroelectrically, and it is the response of the lead iodide, which is paraelectric. Then at room temperature, I look at it. Again, it looks exactly paraelectric. There is no loop opening, like the one that I showed before for the standard ferroelectric. It says it's not a ferroelectric material. If it is not a ferroelectric material, then what are the dipoles doing? I can also look at it by another technique. Let me skip through. It's basically second harmonic generation. Any material which is polar, like a ferroelectric material, has the ability of taking light of one wavelength and converting a part of it, a small fraction of it, into half the wavelength or twice the frequency, higher energy photon. It is called a second harmonic generation, and a very sensitive tool to see if something is polar. And we did this measurement. I'll only tell you the result, that we find the second harmonic generation efficiency is below the detection limit, and our detection limit is 0.02%. Whereas a polar material would have several tens of percent efficiency. Again, showing it's not a ferroelectric material. And what are the dipoles doing? They must be disordered. They can be dynamically disordered or statically disordered. In fact, in order to understand that, what we are going to do is look at this spectrum, this particular plot, which is a dielectric plot. I'm plotting dielectric constant here, temperature here, of one of these material MaPbBr3, which has a dipole at Ma. I can do another thing. I can take out Ma and put cesium there. Cesium has no dipole. It's one metal ion. And then I see dielectric constant looks like this. Rest of it is the same PbBr3. And there is no contribution from the dipole. So when I compare this one with the MaPbBr2, which has the dipole, this part where dipoles are antiferroelectrically ordered, I know. I see that this and this look similar, almost temperature independent. Dipoles are not contributing, which means above this phase transition, where it goes into another crystallographic phase, this very strong 1/T dependence of the dielectric constant is because these dipoles are rotating. It's coming entirely from the dipole. You see, not dipole, it is not there, dipole is there, it's there. So the dipoles are freely rotating in this material. I'll not go into the details. We have estimated from very detailed theory. The rotational time scale is in the order of 1 to 10 picosecond in this material. And this is in collaboration with the Vienna University that I talked about. Another quick, interesting aspect that I have to point out is that, it is true that these are the dipoles that are rotating freely. That's in the ground state, and it's not ferroelectric. But imagine that I come with a photon, it gets absorbed, it creates an electron and a hole. Now this electron will get attracted to the positive end of the dipole. The hole will get attracted to the negative end of the dipole. And then the dipole may not be able to rotate because it has to carry the electron and hole. So it may try to force a dipole to not rotate. And then that dipole, through dipolar interaction, can influence the neighboring dipoles, and I can have a polarization building up in the excited state because of the electron hole generation. We even checked this. The way we did that is after this absorption, we give a time delay and come in with a long wavelength and see if that wavelength is getting converted into half the wavelength or not, telling me after how much time, and I can vary this time. So I can start with something like 80 femtosecond after the absorption to all the way 1 nanosecond, 3 nanosecond after, and you have looked at entire time scale from femtosecond to nanosecond, and we find no second harmonic generation, saying that in this excited state also, there is absolutely no polarity that is developing. I'll not go tell you about this because I've told you the results already. I'll just quickly show you about the excitonic binding energy because I'm running out of time. I'm sorry, I'm taking a little more. It's already 50 minutes that I've spoken. Give me 5 more minutes. I apologize for overrunning.
There is no hurry, sir. Please,
Okay.
go on nicely because I would like to listen to you.
Thank you very much.
If you have a problem, please continue.
Okay, so I want to tell you about the excitonic binding energy. This is our unpublished results, and tell you the puzzle of it and how we try to solve the problem. This is a collection of publications and the binding energy reported for the same material. And you can see here itself from 98 millielectron volt to 6 millielectron volt. So there are 2 orders of magnitude difference between the various estimates, and that's crazy. And that doesn't make sense. We try to understand why this is happening. The way one can estimate the excitonic binding energy is by looking at the photoluminescence. Let me tell you about the basic process. So if I'm not separating the electron and hole with a photovoltaic circuit, I give in light, it creates an electron and hole. That electron and hole has a
What happened?
Network has gone. Possibly his network has gone.
Oh,
We'll have to wait for a while. There is no issue at this end.
he's back.
Yeah.
It is okay now?
Professor Sharma?
I will connect to his phone, he told.
okay, no, I know what happened. Somehow I got muted.
Okay.
There was no problem, but I got muted somehow.
Okay.
Okay, that's okay.
Thanks a lot, Silchar. You really alerted me because you said I realized. Because I could hear you and you couldn't hear me. I said, oh my God, what happened? Okay, I'll go back to the presentation again. I hope you can see.
Yes,
Can you
I can.
Yes.
Wonderful. Okay. So there is a certain binding energy, and this binding energy holds the electron and hold together till they recombine again, giving out a light. This light we call the photoluminescence. Now imagine if this binding energy is comparable to the temperature, so that what would happen, sometimes this electron hole that is bound will get unbound because of thermal energy. It will get excited into the band state where the electron and hole can go apart. So as I increase the temperature, my photoluminescence intensity will go down because of the thermal population of the delocalized unbound electron hole state. And immediately you can see this process can be mathematically expressed. If the binding energy is EB, and if my thermal energy is kBT, then I know that the population of the bound state to the unbound state, what the ratio is. And if that ratio controls my photoluminescence, then the photoluminescence intensity as a function of temperature must follow this equation. So if I now monitor the intensity as a function of temperature, then I'll see that it changes. I'll fit with this, and I'll find out what EB is. It's very straightforward, which is wonderful, and that's what everybody did. And we also did.
This A is a determined constant from the experiment?
No, that also you have to do the fitting. I0, A, and EB are the three unknowns.
I see. Okay.
But you can have any number of observables because you can do many T points.
Yes.
So that the confidence limit goes up. And then you estimate what is the error bar on this. And because only a high energy physicist will catch me on that. Actually, the error bar on A turns out to be large. But a estimate on the binding energy is tight because of the exponential dependency.
Okay.
Yeah, so the dependencies are that way. So you get a good estimate of this, but not so much of this, but you don't care about this one. It is this one that you're after. And if you do the measurement, indeed, this is what I'm showing you, photoluminescence spectrum as a function of the wavelength for different temperatures. And you can see as my temperature start from 155 Kelvin high, 174 Kelvin, 189, and it keeps going down very rapidly. And so I can fit this and extract. But when I do that, there's a major problem. I do it on Monday, I get one result. I do it on Tuesday, I get a different result. I do it on Tuesday afternoon, I get yet another result. Every result is different. And that got us very puzzled for a long time. Because we were trying to reproduce the data. If we had not tried that, if we publish our first set of data, we would have been happy, we would have got some estimate and a paper. But since we tried to reproduce it, we found that our own estimate is all over the place. Then we started thinking what could be the source. Now you see that when you're changing the temperature, how do you change the temperature? You put it on a cryostat, the sample. Now when you put it on a cryostat and you start to cool down, what happens? Atmospheric condensation takes place. Because if you're going to 155 Kelvin, you can imagine everything is condensing on your sample and the sample will get covered. So what is done? And then the intensity will go down. But this is not the case. We are clever. We don't want any condensation to happen. So what we do is we put it on cryostat and we put the cryostat in a vacuum chamber so that nothing can condense because there is nothing. We evacuate. And after evacuation, we did this experiment. One of my clever students actually started doing the experiment without changing the temperature as she was evacuating. And she found as soon as she starts to evacuate, the intensity is going down. And going down very rapidly. Here in logarithmic scale, with the pumping time, the intensity dropped off. That means something very unusual going on with evacuation. But this need not be evacuation. It could also be the time, because in order to do this experiment, photoluminescence, what am I doing? I'm shining light on the substance constantly. If my light shining on the substance is deteriorating, degrading the substance, then it could be the light that is degrading or the evacuation that is degrading the sample. One of the two. And that can be experimented with. What we did was have dark period. Don't do any experiment. Then do the experiment quickly. Then don't do experiment quickly. You can see it's still dropping continuously. Otherwise, it should have continued like this and dropped, continued like this and dropped. It should have done a very different behavior. So it says that it is not the darkness or illumination that is degrading the sample, but it is the pumping time, evacuation time that is degrading the sample. Basically, what happens then, we figured, is that, remember, I have said that this sample is fantastic because it has a very good absorption coefficient. All the photons that are coming in get absorbed very close to the surface. And the surface has a lot of defects. Those defects are normally passivated by oxygen adsorption, some moisture adsorption. As soon as I start to pump, these adsorbed gases are released and they go away, and the defect states become active. These defect states quench your photoluminescence intensity, and that's why with pumping you would go down. That means you cannot pump if you want to do this experiment this way. And if you don't pump, you cannot lower the temperature, and you need to lower the temperature. How to do the experiment then? Then we devised a new way of doing the experiment. It's called the 2-photon absorption. That means I come with 1 photon, which has an energy lower than the band gap. But I provide the sample. So this photon will go through, illuminate throughout the bulk of the material, not near the surface. Its absorption coefficient is very small. So it will illuminate the entire sample. But I'll provide many, many of these photons, such that there will be small probability events happening throughout the sample where 2 photons will combine simultaneously and give rise to an absorption, because 2 photons will have enough energy to excite the electron. And then this absorption is taking place deep inside the sample, throughout the sample, and the photoluminescence will take place deep inside, and it is not going to be sensitive to the surface defects. And then I can pump down and nothing would happen. And that's the kind of experiment we did. And these are very stable data. 2-photon absorption induced photoluminescence, and then we see how the photoluminescence changes. Then we extract the number, and the numbers for 2 different measurements is 55 MeV, 46 MeV for 2 different samples of the same composition. That tells you the sort of error bar. So it's 50 plus minus 5 or 6 millielectron volt is the excitonic binding energy. We estimated for several compounds. In fact, in collaboration with the Vienna group earlier, we had estimated from very sophisticated, very large-scale computation what the excitonic binding energies should be for all these materials, plotted as a function of calculated band gap and the excitonic binding energy. And we have estimated now from the experiment for this one, FAPB-I3, MAPB-I3, FAPB-BR3, MAPB-BR3, as well as some of the cesium compounds. And I'm going to show our estimates. These are the estimates. You can see, compare very well to MAPB-I3, and this is the MAPB-BR3 and MAPB-BR3 theoretical estimate, showing that now we are getting reliable values. So with that, let me come to the end, giving you the outlook of this wonder material. There are many other questions. I've told you very small snippet of our excitement of this material. There can be just on this material, on its surprises and its fascinating properties in every respect. There can be several conferences run. And in fact, there are several conferences run every year with thousands of participants. Such excitement is going on in this field. But let me end by giving the outlook. The efficiency improvement has been fantastic, and it has impacted the economics of production. The energy audit, I told you that it costs very little energy to make these PV modules from these materials because it's solution-based, and that's why the energy audit will favor this particular technology. It's unlikely to replace silicon technology because silicon technology, there's billions and billions of dollars have been invested and the industry exists. So the first line of implementation that is coming is actually in tandem structure. where you take the silicon technology, silicon solar cell, and put a coating of this on top of that such that the efficiency goes up significantly. And that's the real technological possibility and the most likely thing to hit the market soon. And there's a great excitement ahead in this field. Also, let me tell you the difficulties. The stability is a real difficulty, but to a large extent, it's being addressed. Presence of lead is also a question. That is also being addressed. In fact, last week we had a conference devoted to this particular material, and one of the world leaders from Oxford who are driving this tandem structure presented new data where lead is all but replaced by tin, and yet giving enough efficiency to be commercially viable. And defect control, which tends to lower the efficiency, increase the many bad aspects, is also a problem. This is a comment that I'll not elaborate on. There's another fascinating science aspect related, that it seems that though it has defects, these defects are not as disastrous as they are in other semiconductor technologies. With that, let me end thanking you for your attention and your patience. Thank you very much.
Thank you, Mr. Sharma, for this wonderful talk. Now, somebody is requesting you, can we see the material really? Do you have a photograph of whatever, like the synthesized, like this?
It's a very good question. Okay, please send me an email. My email ID, you can find it very easily if you give a Google search, and I'll send you some nice photo. We have made single crystals also of this material. Let me first stop. Have I stopped the presentation? No, I'm still presenting.
No, you are still presenting.
Okay.
Yeah, now it's okay.
Okay, so send me a request, and I'll definitely send you photographs of it. I'll request one of my colleagues, one of my group member, to send you the photos. Often in this particular slide section, I don't have one. I should have kept one. I should have anticipated.
Yeah, so Mr. Sundar Arvind, you please write a mail to Professor Sharma. You can have a like glimpse of whatever you want to see, and then like Nilotpal Bhattacharya is requesting you. Can you kindly re-explain that part where you explained the unreliable results?
Okay, for the excitonic binding energy, right?
Yeah, possibly, yeah.
Okay, so let me then.
Participants, put questions only. Don't write thank you. Like I'm trying to put questions.
Okay, let me make a presentation quickly, and I'll explain to you using the presentation. Where is my presentation? Why doesn't it show? No, it's not showing. Wait a minute. I'm trying to get to the presentation so that I can use a slide to explain to you. Yeah. Okay, you can see the slide. I had shown you this slide before. There's one slide hidden that I didn't show. I showed you this. So basically, the problem is when you put it into the evacuation so that we can change the temperature, the experiment requires changing the temperature to record photoluminescence spectrum as a function of temperature. In order to change temperature, I need to put the sample in an evacuated place so that condensation doesn't take place. But when I evacuate, see the photoluminescence intensity at one given time, temperature also is changing. So whether I start the experiment at this point to change temperature, or this point, or this point, or this point, or this point, what would happen is that there is an effect coming from the evacuation, changing the photoluminescence intensity, another temperature also changing the photoluminescence intensity. One can say, okay, then come to this end where the photoluminescence intensity is not changing anymore and do the experiment there. But you see, then you have so low intensity that your error bar becomes very, very huge, and you get very unreliable data. And here is actual attempts of ours of trying to do before we realized different days. It's the same MAPBBR3. Different days we did the experiment, and this is a photoluminescence intensity as a function of temperature. And you see that each of the run look different. And if I fit it, I'll get different numbers for the excitonic binding energy. It is because we were doing the experiment at different points on this curve. You understand? So that's the reason. I hope I've been able to explain.
Is it Nilafal? Is it like, are you satisfied? Because he was asking for a reason in brief.
Yes,
Yeah.
Thank you, sir.
Welcome.
Okay. So, like Atwar Rahman is asking, sir, although the efficiency of perovskite solar cell is greater than the silicon solar cell, but the lifetime of perovskite cell is low because of moisture problem. So, how can we minimize the moisture problem or decrease the degradation of the surface, basically?
Yeah, this is the point that I raised in the outlook. The stability is an issue, but today there are 2 or 3 different approaches. One approach is by substitution chemistry. People have been able to make things that are fairly stable for a very long time. Okay, not compared to the silicon solar cells. In fact, we don't even know silicon solar cells, how stable they are. They're supposed to have a life of 25 years. Nobody has done the checking of that yet. And they actually collect so much of dust and other things that it's not the degradation of the module, but for some other reason it stops working. So long-term stability is an issue. One aspect is substitutional chemistry, by which people have been able to increase the stability very substantially. And the second is that after that, you can embed it. You can have a polymeric film on it so that it doesn't get exposed to atmospheric conditions. Okay? So there are many different technologies that can be brought in order to be able to protect it from things that causes the degradation. Okay?
So at this point, Manoranjan Kakoti is asking, what is the stability of a perovskite cell, sir?
Oh, I mean, there are many, I mean, the ones that are claimed to be stable, I think thousands of hours. Since I don't work in that area, I have not kept up with the literature, but I think it's in units of thousands of hours.
Okay. Okay. So, Devalina Sharma asking, defects are good or bad for the perovskites?
By the very name defect, you won't call it a defect if it is good. So defects are also bad, but it turns out it's one of the scientific puzzle that people acknowledge and think about, wonder about. It seems that the properties of, for example, silicon solar cell would be very strongly affected by a certain concentration of defects. At the same concentration of defects, this perovskite solar cell seems to be completely impervious to defects. So they have much higher tolerance against defects.
Steady at some point. So I think, Devalana, you have got your answer. Then Rosa Ramani Gavara, it is he or she, I don't know. The question is there any possible element that can replace lead in
there's a lot of study with tin in particular, and I pointed out that last week in the conference, Henry Smith talked about a compound which is almost completely tin. I think had 5% lead only.
Okay.
Okay, but also don't forget, I mean, this question comes up very often that lead is there, so it will not be used. You know, all your car batteries are lead acid batteries.
Yes, no, that is true. So Sheen Venkat asks, does a fully inorganic perovskite ABX3 in cubic structure can have the novelty you listed experimentally? I am doing computational research. What is your suggestion on studying such material computationally?
First of all, there's a lot of study specifically with cesium. It's known that the cesium supports a perovskite structure. So you can, and I also showed some dielectric study data of cesium compound. So it exists, and people have explored photovoltaic response of cesium and also other interesting applications. So pure inorganic also exists, the counterpart, and they also have similarly interesting properties. They are not as good as the hybrid ones yet, but they are sizable. And what study to do is a very difficult question to answer, simply because it's such a hot field. Very large scale calculations have been done. So one needs to be clever about where you have to have a right question, really. See, you should never ask the question that, can I do this study, can I do that study? What you should ask is that, is there a question that you are interested in, that you are motivated to understand the reason for? If it excites you, it is worth doing, do it. Find out every which way that can be done. Don't be limited by what technique you have. But always approach it from a fundamental curiosity inside you to drive you to a problem, rather than saying, well, somebody has published, so many have published, I can also do something and publish. That doesn't really, it's nice to do that, to learn. For younger people, I don't want to be, I don't want to put them off or put them down. It's nice to learn a field and to do such research, but eventually do something that you're passionate about, that you really love doing. Some question that drives it. Okay?
Yeah, so Ashin, I think you have got the point. So once in a field which is very forefront area, what sir is telling, that it's very important to ask the right question and then to pursue it.
Yeah.
So
Thank you.
yeah, the next question is by Rangaraj, who has asked, what is the role of perturbation theory in photoluminescence or thermoluminescence study?
That's a somewhat strange question. Is because did I talk about perturbation theory in the context of photoluminescence and thermoluminescence? Yeah, because I'm not sure I understand the nature of the question to answer it.
I can just pass the question, because those people are doing some perturbation theory somewhere. They're telling me that they can drag the perturbation theory there. Just pass on the question. Just go ahead. Ask the different question now. This question.
Yeah, that's true. Yeah, but another question is there, which also, I mean, Chayanika is asking, what is the causes for energy crisis in India? It was been discussed, Chayanika.
Yes. Yes.
Yeah, so at some length, Mr. discussed it already. So these are the questions probably I had today. Anyone else want to ask anything? Utpal, Jyotirma, you want to ask anything? Yes, Jyotirma, yes.
No, ma'am.
Utpal, you want to ask anything? You want to discuss?
Sir, actually,
Utpal Sarkar, who is a faculty member of the department, he actually pursues some work in this area.
Okay,
So
very nice.
I request Utpal to please.
yeah, sir, regarding these perovskite structures, you have already discussed actually, but again, these inorganic structures which contains these metal substances, does it not more toxic or than the organic one? So, in that respect, should we go for perovskite as sorts of hybrid structure, incorporating the organic substance, or only for the carbon-based organic materials? For though these carbon-based organic materials have less efficiency, but during the sustainability purpose, these are less toxic. So, which is your opinion?
Actually, with respect to this particular lead halide perovskites, it turns out that the hybrid materials are less stable. The cesium lead halide is more stable than the hybrid one. Hybrid also, the Ma is very unstable. The Fa, formamidinium, is more stable, formamidinium analog. And that's why people, what they've been doing is to reduce the Ma content and put a lot of Fa and a little bit of cesium to make it more stable. Pure Ma compound is the most unstable in general. It's very susceptible to water, humidity, it degrades, it gives out lead. Also, it gives out lead iodide and it gives out HI, the acid. Okay, so it's I would say that one. But eventually, those are very important questions and to be answered before the technological applications come. But I think we also have a lot of interesting questions, and there you don't have to worry about, as long as you are following safety norms properly, you should do the basic science irrespective of whether they're toxic or not. Because there's a lot of interesting science to be learned, which then can help us with the other areas as well.
Nice. And sir, another question. In the simulation purpose, usually we take only one unit cell of this structure or a supercell like structure, but that does not mimic the actual experimental conditions. And so we get a huge order of difference in our results compared to the experimental one. But the nature, if says, well, then we say, okay, it's matching. But is it, we are forcibly telling that the theoretical results are matching to the experimental one, or is it the right science we are doing?
There's no one single answer to that. First of all, is most of the serious theory work on these materials actually work with very large supercell. Very, very large supercell, not even, I mean, small. It's our own work consists of at least, I mean, the minimum that you need definitely is 8 unit cells, 8 primitive unit cells, but most of the simulations are done with a much larger one. So you need very large supercell to describe very often. It depends a little bit on what you, I mean, this is a question that is applicable to any material, not only this. So depending on the science that you are interested in, you may have to use different size supercells. And of course, you have to keep in mind the limitation of the computation that you're doing. Because remember, you're trying to describe a material with Avogadro number of electrons.
Yes.
And you're doing a one electron theory at the end. Right?
Actually, sir, my question is that regarding when we are doing the stability, that times we are only calculating the energy. But in the solar cell calculations, we have to we are calculating the optical properties, which need some sort of perturbations and optical calculations, which are very precise in nature. That times we have to reduce the supercell. Otherwise, the computational resource will be lower. So that's why I'm asking. So what is
I fully understand, but let me tell you our experience, because we had a lot of experience with that, with the Vienna group. When doing the excited binding energy calculations, basically any optical calculation that you want to do is an excited state calculation.
Yes, sir.
It's not a ground state calculation anymore.
Yeah.
Which implies that it's a very complex calculation. Excited state calculations, if you try to do it phenomenology that is good for ground state, you will just not get any result that is of any meaning, right? So,
yes, sir.
In fact, excited binding energy, we had to do Bethe-Salpeter equation solution, and these are very complex, and yet we had to do the calculation for a very large number of K points, which is equivalent to what is the supercell size that you're talking about, because if you do very few K points, then it didn't convert.
Hmm.
And in fact, the biggest supercomputer in Europe that was available was near the saturation point for those calculations.
Yes.
For us to be able to convert that. This was driven by the Vienna group. I was a visiting professor there at that time, and we collaborated on this. And then Mendo Bogdan and our group together, their group together, we published several papers which I have cited. You can look them up.
Okay, sir. Thank you, sir.
Another question by Ashira Shaikia. She is asking what is the possible solution for this energy crisis? Can we solve it permanently? She is asking.
If I had the solution, I'll not share it with anybody. I'll just commercialize it immediately and be a very rich man. Okay, jokes apart. I mean, again, it's these small efforts from all around. We don't know where eventually the solution comes from. We keep trying in different directions. Something clicks. We take one step in that direction. For example, I mean, photovoltaic, when it started, nobody believed that it's going to be commercially successful, right? And today, photovoltaics are commercially competing with the fossil fuel route of generation of electricity, or even lower. Wind has become lower than the conventional source. So these involve research discoveries, innovation, and painstaking improvement of efficiency and reduction cost of production by scaling up to make it successful. Hopefully, electric vehicle is one of the things that people are betting on, which will require revolution in storage technology in batteries. Hopefully, photovoltaics will be able to take the load off fossil fuel. We are hoping for that. But that will also need very large-scale storage technology that we don't know about as of now. So I think there's still some excitement to come in the future.
Atri, don't take too many questions now. It is getting late.
It's quite
late. Yeah.
I just there were not.
No. You can always ask the people that they will say mail and he will write. I am 100% sure about he will explain if the question is making sense. And so you can declare it and now bring it to a close because it's Saturday evening and getting late. Yeah.
Yeah. Of course. We planned for about 1 hour. Now it's going to be 1.5, more than 1.5 hours.
Yes.
Yeah, I'm very sorry, Professor Sarma, that we are taking that 40 minutes extra from your.
I took 10 extra minutes also. So
it was a wonderful experience, and so this energy materials and how they can help, and these are some very direct practical applications. And I really wish that in department I know a few students are working with Dr. Utpal Sarkar, and I hope that they will get back to you some point of time for some discussion or something, whatever.
Sure. And I would hope to come and visit them sometime when the situation is
hope
better.
really so, because of this COVID got messed up. I hope the situation crisis will be over soon and you will be able to really physically visit the department.
I would be very happy.
Yeah, and I see that chemistry department is also here,
I'm sure that the COVID crisis will be over, but energy crisis will remain. But during that time, you have a meeting.
It is not going very soon.
I will request you and your department to have a small meeting, focused meeting, 10-15 people, not 50-60 people. Invite Professor Sarma and some other colleagues. They'll spend, if your people are interested, have detailed discussion, they will review what has happened, but they will also discuss about how to go forward. That's the only way we can do something good for our country. And instead of asking that when the crisis will be over, this will happen, that will happen, that is not the point. We all are trying in every field, we all are trying. And this is the most crucial issue as far as internationally we are concerned, the energy crisis. As it was explained from the beginning, without energy, there will be no life in our planet.
Yeah.
So this cannot be addressed or discussed out in a 2 hours meeting, 1.5 hour meeting. Professor Sarma has agreed to come there. So come up with a proposal, but make it a focused meeting.
Yes.
It should not be like a DAE meeting that you come in 5 minutes.
Hey, Sudhakar, you'll get into trouble with your parent organization.
Yeah, I know that I do that.
So the point is that actually this is a public talk. We wanted people to get interested in this topic so that people can take up some serious work.
No, I'm very happy that you are making this public talk. For example, today's talk, as I understand, the public talk is not Professor Sarma talking. What I understood is that someone is talking, some students will be interested to think about these issues.
Yeah, that is the main aim actually.
And that I am from the beginning. In fact, 1 hour before the talk started, I had already switched on and I was waiting. So that part has been done. But now you find out if that there are issues really, which I myself is trying. I am not getting support. I didn't get that support in Institute of Physics, my faculty wanting that we have a focused discussion on this. Neither in Niger, I am getting that request that let's have a focused discussion on this. And this is what I say. Only if we have a focused discussion with 10 people for 3-4 days, then we can make some progress. All conferences giving 10 minutes talk, someone gives half an hour talk, someone gives 10 minutes talk. That's not going because they will show up what they have done. That will not take anything forward. If you think, we'll try to find out where from the budget will come. You can request Professor Sarma to help us in organizing this. And if there is interest in locally, in that area, then we can see. And since I know at least government is sympathetic for Northeast region,
Yes.
so
Yes.
even establishing a research center on this area will not be very difficult. If there are leadership coming up from that area. So think about that. And as for the students, I'm very happy we're asking questions, and Professor Sarma is a person who is a down-to-earth person. He will reply all the mails, provided we have definite questions, not the drum questions, then none of us will pay attention to answer to that. Beating the drum questions we don't like. If any question, even if it is silly question, but that he will answer. That's no problem. Okay, Atri, now you can conclude the session and let Didi go home. And Didi, are you at home or you are in the office?
I am in virtual world at home. I've been working from home.
At least good that you don't have to drive now back home.
No, that's right.
Yeah. So
we are at the end part of the story. So I would like to thank again Professor Sharma, and I would like to request our HOD Indrajit Sharma sir to formally say the thanks note in on behalf of the department. Professor Indrajit, are you there? He is there, but I don't know, there is some issue. I think we will stop here. I would like to thank everyone, not only the speaker, because of him we are here anyway, but the speaker audience is also important, and I thank everyone for being here this evening with us. And we hope to organize